Hey, so today I'm here to talk to you about how Equinix Bare Metal Cloud keeps up with all the new OS releases. But that's kind of a mouthful. Put simply, I'm going to walk you through how we automated our OS image builds using Buildkite, and why we chose Buildkite for the system. But first, a little about me. My name is Sarah Funkhouser, but known at work as S-Funk. I'm a software engineer, recently turned engineering manager, working at Equinix Metal. And before you ask, yes, I still write code, actually lots of it. But I've also been given the opportunity to lead other engineers, something that honestly scared me when presented to me a year ago, but I've kind of fallen in love with it. When I'm not working, or even when I am actually, I have two elementary age kids, a girl and a boy, that constantly keep me on my toes and are currently staring at me through my office doors. I'm a dog mom of three, which you also can't see, but there's one to my left, one to my right, and one behind me. So hopefully you don't get any deliveries for the next 15 to 20 minutes. When I get some time on my own, you can usually find me running, although I recently found a new love combining that with cycling and swimming. But that's enough about me. Let's talk about the fun stuff that you came here to listen to. As I said, we're here to talk about the automation of OS images. But why does Equinix Metal care about OS image builds? For those new around here or just haven't heard about Equinix Metal has servers, lots of them, and we allow customers to provision these bare metal servers on demand. We offer a wide variety of OSs for the servers, and we need to make sure those images are up to date. Not only that, but customers have an expectation that an Ubuntu image is an Ubuntu image. No extra packages installed, and it works similar as they would from another cloud. We don't want extra bloat running on these images. So part of this effort was to align our bare metal OS images with upstream cloud images as close as possible. These can't be one-to-one in a lot of cases because there are packages that could be required on a bare metal server that aren't needed in a virtual machine. So as part of this, we set out to solve a few problems. The first was a reliable release cycle, not just when an engineer had time in their sprint to build and test new images. We wanted to target this once per month, and as we onboarded more and more hardware, this wasn't sustainable or scalable with the current setup that we had. We wanted as little human involvement as possible. We have a lot more complex problems to solve, so we wanted the computers to take over in this case. And lastly, we wanted tests. If we add a new piece of hardware with a new NIC, the test should be able to handle to make sure that the network works. Can you still SSH to that server? Just some simple set of tests to start, just to make sure that we weren't releasing bad images to customers. So how did we do this? Well, before we talk about what we do today, let's talk about what we had before. The existing setup when I first started taking a look at this project was using Packer for Docker-based image builds. Now, as I said, we wanted to make sure that we were aligning with the upstream cloud image. So getting rid of Docker-based image builds was one of the key parts of the criteria of this project. We also wanted as little human involvement as possible, and the current setup required a lot of manual human testing. So the CI that existed in place would create the image, publish it to Git LFS, but then an engineer had to take that, provision pieces of hardware for every plan that we wanted to release to customers. It was also a lot of clicking in the UI to enable it for different plan types, which also lends itself to mistakes when you have to manually click on buttons. When I started at Metal, the only CI really in use was a very old version of Drone that required a net new deploy and not just an upgrade. It meant updating pipelines no matter if we upgraded Drone versions or if we decided on an entirely new CI system as well. So, since we needed a new CI system no matter which way we went, one of my first projects at Metal was to pick a new CI system for the organization. Well, how do you pick a new CI system? Well, I chose one of the hardest problems we wanted to solve and try to solve it with different CIs. I looked at a few systems. The newest Drone, we had engineers comfortable with Drone, so it needed to be one of the systems we looked at. GitHub Actions, came with our GitHub Enterprise contracts, so it's already built in. Let's see if this will solve our problems. Concourse, because that's what I used in my last company. Really enjoyed it for different pieces of just your basic Docker builds. And Buildkite. We got it down to just a GitHub Actions and a Buildkite POC. GitHub Actions, as I said, it was already in our GitHub Enterprise license, and to be honest, I really wanted to solve all our problems, but it didn't. So why Buildkite? Buildkite is predictable. It's just Bash. And so whatever you write on your laptop, you can run it, and it should work the same way in Buildkite. It's easy to deploy self-hosted runners. As I said, we have servers, lots of them. And Buildkite takes advantage of that, whereas other CI systems could be pretty limiting. It's secure. We love that our internal testing isn't potentially exposed. And debugging a broken build is simple, which is great because preparing OS versions isn't. When we started using Buildkite for some of our We even started using Buildkite for some of our open source projects. Buildkite offers free accounts for public builds, which we love. That way we can use the same CI for our internal projects as we do for open source projects. So where do we go from here? Well, we needed to build new OSs. I'm a Golang developer at heart, so what do? I wanted something that I could run on my laptop, not just in CI. And as I said before, Buildkite is just Bash. So how do we combine these two to make it easy for everyone? Well, I built a Golang CLI to handle all the hard parts. Golang allowed for the portability as well as unit testing of the code I was looking for, and integrated into some of our existing Go libraries, particularly with our API, to make new OS versions available to customers. We are also a Golang shop, which means almost all new development is in Golang, so I wanted to use something developers were comfortable with. With the CLI, there are a bunch of different commands that it offers, but we're going to look at two of the most critical ones for this project, the first being customize. As I said, we previously used Packer for our OS image builds, but these images were Docker-based images, which meant it didn't hit one of our key features for this new system, which was aligning with upstream cloud images. I started looking at Vert Customize because this allowed us to easily customize a virtual image in place, making installing required packages a breeze, and the integrations that they had made it really easy to do a lot of the configuration changes we needed. This command is fairly simple. You give it the command, so the Golang CLI in this case is called Bob the Builder. The command here is customize. And then we only need a few command line arguments. In this case is Alma9, and this is an ARM build, so it's Arch64. But this doesn't seem like quite enough to actually build an operating system. So how does this work? Well, those two flags end up being able to point to a YAML configuration. You can either, in this case, you could pass it just these two flags, which made it easy to integrate into our CI system, but you could also pass an entire template path instead. The template in here, we decided because we're using YAML for so much other stuff, we're a Kubernetes shop, why not use YAML for the config here? Because it was easy to work with for the most part. So let's take a look what this YAML config looks like. This is a fairly simple one. You'll have four main sections. The first being the name. This is a human readable name that can be used throughout the build process. The next are some build configs, but generally these use the defaults. And so we don't actually touch these very much. One big change we would do here is if we're trying to debug a failing build, we would change that debug flag from true to false. This is also enabled within the CI system itself, so you don't actually have to change the template to be able to do this. But now we have the good stuff. The bulk of this is in the image section. The image will redefine any customizations we might need on the image. The most important one here being the upstream cloud image. As I said, we want to be able to pull an image straight from a cloud provider, or straight from the operating system provider. In this case, this is Alma Linux, but we also pull the Ubuntu images, etc., directly from the URL, which means that as they update the image, our next build will pull that latest image. In this one, you see that we're not actually making any other real significant changes to the upstream cloud image itself, but there's a lot of other features you could change. You could add extra packages, which usually the base packages in this case are stuff that was required for that operating system to work at all on the hardware, whereas extra packages are stuff that customers want installed, but aren't necessarily part of the default upstream cloud image. Things like additional commands allow for any command to be run to configure the image, which has proven to be especially helpful with issues with Grub. Now, as I said, this is a pretty simple one, but if you looked at our Ubuntu config, there's a lot more stuff going on there, particularly to install extra packages for things like we need for drivers, like for a particular NICs that we need, and it's not in the default Ubuntu install. Finally, the last section here is provisioning. As I said, we have lots of servers, while we also have a lot of plans, and those underlying hardware are different. This particular image is for ARM, which we only have one plan currently for. But if you look at our x86 builds, there are about 10 to 15 plans per OS image that it needs to be tested for. As I said, we're not doing this manually. We want the computers to be able to do this for us. So here you can provide a list of supported plans, and as using Buildkite dynamic pipelines, we're easily able to provision and test the image per plan. So now that we have our image, which is exported to the format we need for our provisioner, we also need to make sure this image is available to customers. The publish command allows us to publish the image to both Git LFS, which we use for a lot of our CI testing, as well as S3 buckets for consumption by a provisioner. Again, it's just a few command line flags. In this case, you have the publish command that comes after the name of the Golang CLI. You give it a name, you give it the image directory where the actual image that was created by the customized command lives, and there's an option to flag to publish to S3. When we first started this project, we were only publishing to Git LFS, but we converted to S3, and so this allows you to publish to both places. Speaking of Linux OSs, when we first built this, it was used just for Ubuntu. But now, with the flexibility of just requiring a YAML template, we now support 6 other Linux distros, including Alma, Alpine, CentOS, Debian, Red Hat Linux, and Rocky. These all work, for the most part, for both x86 and ARM, just by adding a new YAML template. We also, for some types of hardware, we needed extra packages, and we didn't want these installed on every plan, and so you're able to create multiple templates per operating system and allow for extra packages to be defined per set of hardware. So let's look at the pipeline itself. As I said, we've kind of been talking about how you can run this on your laptop, but obviously we run this in Buildkite. So what are we taking advantage of there? Again, we're looking at a very simple use case here where we just have one supported plan. You can see that first we build the Golang CLI for the architecture that we need to run this on. So whenever we're building something for ARM, we run it on ARM hardware, whereas whenever we're doing it for x86, we do this all on x86 hardware. So in this case, you'll see the build of the Golang CLI for ARM. And then we go through that template, the YAML template as I showed before, and pull every supported plan that we're going to need. Next, we build the image using that customize command, and then we're going to push the image either to Git LFS or S3, depending on which part of the process we're in. And now we can take advantage of the dynamic pipelines that allows us to create the test, the provision, the test, and the deprovision for each plan defined that we had grabbed in that step 2. Now let's talk about the provision and deprovision. At Metal, we need to do a provision to test not just OSs, but a lot of our software. And we are all about reusability. So instead of just writing more bash that would be copied and pasted many times throughout CI, we took advantage of Buildkite pipelines. We created both a provision and deprovision plugin that allows us to specify just a few key fields and have this plug into any pipeline as we want. This allowed us to not only use in operating systems, but we have a canary that runs the provisions lots of hardware all throughout the day, so we can make sure that if something changes, we could catch that in the canary pipeline. We use this in our provisioner testing as well, and as multiple projects throughout the organization. All you have to do is you give it a project that you want the hardware to provision in, the plan that you want it to provision on, the operating system, pretty critical in this pipeline. You can also, this uses the default image that customers provide, but you can also provide flags to override with your custom image that was created as earlier steps in the pipeline. And a key one here is the TTL for this hardware. This is important because if a pipeline failed and you never hit the deprovision cleanup device step, your hardware would be lying around and require human involvement to clean up. And we want to make sure that it's not just sitting there. And so the TTL allows us to say, after the switch time, deprovision that hardware. Now, the example we saw earlier, we only had one plan, and so it'd be pretty easy to look at that pipeline and see why it failed or why it didn't. But as I said, a lot of this is probably 10 to 15 plans per OS, and we don't want to have to dig through lines of code to see what happened. We want to look at the pipeline and say, oh, all these plans passed, but this one failed, and why? And so Buildkite annotations allows you to easily propagate those failures to the top. And so we can not only propagate them, but we can link them to our Metal CI, which allows us to see the hardware that was provisioned and any logs that went along with that provision as well. So we have a pipeline. So how does this run? There's a few ways. The first is anytime an image template is changed or added, a pipeline per template change is triggered, which means that we're testing the code of the repo first, but then anytime that template changes, that triggers a OS build and publish as well. And so if you want to update an image for that particular image, or if you just wanted to add a particular package, as soon as you made that commit on a PR, it would trigger that pipeline build. And then once that was merged to main, it would publish new images for the customers. We also wanted, as I said, we wanted to be able to have recurring publishes of images on a schedule. This the Buildkite feature of scheduled builds allows us to do this, which means that we're publishing new images at least once per month based on these scheduled builds, as well as anytime engineers need to go make changes to these images themselves. And finally, one of the most unique features I found in Buildkite when evaluating systems was the UI, where we can have a UI entry point to trigger whatever we want that's in that build system. So in this case, a user can go in, choose the OS, choose the architecture, and choose the set of plans, and that will run based on that configuration, rather than what is in the YAML configuration in the Git repo itself. So to wrap up, I just wanted to cover two of the main features that I wanted you to make sure you took away from this. Number one, portability. A few things that come to mind here is first the Golang CLI, Bob the Builder. This means I can build OS images for x86 today on my laptop, different for ARM. You need to run it somewhere where your operating system is, or your architecture is ARM, which makes the development of both the tooling and the operating system smooth. Again, the pipeline steps are just bash, which allows me to debug these steps easily. And finally, the Buildkite CLI command allows me to debug parts of the pipeline locally as well, and not have to push every change to Git as I'm testing, which is a huge win for Buildkite CI system. Next is the reusability. The Buildkite plugin ecosystem has allowed us to configure similar steps in multiple pipelines without copying and pasting. We built a Metal provision and deprovision plugin as part of this project that has been able to be reused throughout the organization in multiple CI builds and ensures it's up to date with the Metal API. Thank you for your time, and you can find me out on the internet, usually under Sarah S. Funkhouser.